All right, thanks for joining me again as we do one other video about the periodic table. Again, we're doing what are called trends, and these are when we look at patterns on the periodic table that are related to some other things. So let's get right into it. Kind of what we're looking for today is what are some other patterns that are found on the periodic table. We may have already, depending on the videos you've watched, looked at valence electrons and structure and so forth. But these other patterns are related to valence electrons and structure, but have some different terms. So some of the vocabulary that we're going to see today: atomic radius, electronegativity, reactivity, and ionization energy. So we'll have slides on each one of those coming up here shortly. All right, so starting with the atomic radius, the radius is a measure of half the distance across a circle generally. And so when we're talking about the atomic radius, pretty much just talking about how, the physical size or shape of the atom. And if you think about how the periodic table is arranged in increasing atomic number, which kind of correlates with increasing atomic weight, you would think that the atoms would just keep getting bigger and bigger and bigger. If you look at the chart on the right, you do see that they do get bigger, but not uniformly. They don't just get bigger and bigger and bigger. So the patterns that we see is that they do get bigger as you go down the group. So if we look in column 1, the alkaline metals, we start with lithium. We're actually at the top with hydrogen. And it almost looks like a piece of candy. It is getting bigger as you go down it. That should make sense because you've got more protons, you've got more electrons. There's just more stuff, so we would expect them to get bigger. The weird thing is when you look at it going the other way, the actual size decreases. All right, so our trend on this, if you look at the arrows going across the top, it says increases, and going down the side, it says increases. And so this one seems to make fairly good sense. This one almost seems backwards, that we would think that since the atoms increase in their atomic numbers and weight, they would get bigger this way, but they actually don't. So what's going on here? There is a little bit of an explanation to this, and you got to think about what's going on as you move across the periodic table from left to right. Every time we go from left to right, we're adding a proton and an electron. Remember, they have opposite charges, and so they tend to pull a little bit more. So even though there may be more electrons and there may be more protons, in terms of the spacing, they actually get pulled in a little bit closer. So as we move from left to right across the periodic table, the size kind of gets compressed. In effect, they get to be a little bit more dense because they're going to be compacted together. But that last shell, remember that all of these would have the same number of electron shells. It's just that as you get more and more electrons, that shell gets to be closer and closer in, and it doesn't take up quite as much space. So this is the one that's a little bit hard to remember because you just think they would get bigger as we go across. The second one is about electronegativity. That sounds like a pretty big word, but if you look at just kind of how the words fit together, electro and negative, and so it has something to do with electrons. And specifically, it's how much an element will actually attract an electron. How much is it going to pull onto it? So let's think back to maybe some things we've already gone over before. Remember, as we go across the periodic table in this direction, we're going to be adding more and more electrons, and our valence shell gets more and more full as we go across to the other side. And so this kind of plays into why you see these little bars being represented higher as we get over to the upper right-hand side, is that they're going to be pulling on electrons way, way more. So effectively, when you get over here to the top, let me get out of the way, fluorine's at the upper right-hand corner. It tends to be the most electronegative of all the elements that are there. And again, think about valence electrons. It's got 7 valence electrons. Everything in this last column has 7 valence electrons. And it's really just, it needs that one last electron to fill up its shell. And so it's got a great deal of attraction for that very last electron. Fluorine ends up having the most because its shell is closest to the nucleus. And so remember, again, the nucleus has the positive charge. And if it's pulling negative, they're going to be attracted. And so fluorine's got the greatest electronegativity out of all the ones in this column. Again, you can see when you get to the bottom, they're still pretty electronegative, but it's not near as much as fluorine. And again, that has to do with how far away that outside shell is going to be. So kind of our trend is, if you look at the periodic table, as we move to the right, and particularly as you move to the upper right, these tend to get to be more and more electronegative. Ionization energy is pretty much the same trend because it has to do with kind of the same thing. So this would kind of be the opposite. This is the energy needed to remove an electron from an atom. And again, fluorine, neon, helium, these are going to be the ones, these would be the hardest ones to remove an electron off of because they tend to do the opposite. They're attracting electrons. If we go back over here to the left-hand side, remember these group 1 elements, they've only got 1 electron in their valence shell, so they can get plucked off pretty easily. So the pattern is really similar to the last slide with the electronegativity. It's really hard to remove an electron from a full shell. It's really hard to remove an electron from an almost full shell. And we find those elements over here on the far right side. So again, our arrows point on this slide just like they did on the previous one. Our final one is reactivity, and reactivity is simply the idea of the degree to which an atom will undergo a chemical reaction. Does it stay like it is, or does it want to join up with someone else? And this is an interesting trend as well because the arrows go in kind of a couple different ways. So the idea with reactivity is the closer we get to the edges of the periodic table, the more reactive our elements tend to get. If we look at the left-hand side, and we see the most reactive of all the elements that we have over here, we tend to see that francium is down there. So let's think about why is francium super reactive? Well, it's only got 1 valence electron, right? And which means it wants to lose that 1 valence electron. And that 1 valence electron, which has a negative charge, is really, really far away from the nucleus. So it's kind of easy for it to get plucked off. If we go all the way to the other side over here, and we look at probably what's the most reactive nonmetal, that would be fluorine. We can move this out of the way so we can see fluorine. Fluorine would probably be our most reactive over here. And let's think about why that is. Fluorine's got 7 valence electrons. And so it's got room for 1 more. It goes back to that whole thing about being the electronegativity. It wants to gain 1 electron. And that 1 electron is going to be really close to the nucleus. And that difference in positive and minus charge is going to pull it closer. So there's a reason behind this arrow. And if you can remember the reason behind the arrow, then it's kind of easy to remember the arrow. So again, francium would be the most reactive metal. Fluorine would be the most reactive nonmetal. And then the last thing to remember is we do have a column over here that's not going to be reactive at all, right? Remember those noble gases, helium, neon, argon, that very last column, their electron shells are already completely full. So they're not going to be doing anything with the electrons at all. And so they're totally non-reactive. So even though this arrow is moving to the upper right-hand corner, it needs to stop before it gets to that last column because the noble gases are not reactive. All right. So in summary, most all these trends are related some way to the electron structure, and if we can remember the electron structure, it's going to help us out. The electron arrangement is in a pattern on the periodic table, and if we can remember that electron structure and the structure of the atom in general, it should help us to remember how these patterns should go if you just don't want to memorize them. Thanks for being with me.